Another key technical challenge in multimodal is alignment. Alignment comes in many different flavors and many different applications. In fact, almost all multimodal problems will have an aspect of alignment. So, for example, in media description, like image captioning, you want to know which object relate to which words, or in a video, which element or which event relate to which phrase, part of a video caption. Modality transcription, like text to speech, or even like generating gestures from speech, will also require this alignment because gestures are not always aligned perfectly or synchronized perfectly. And in many of these new applications, like navigation, question answering, you need to have like where's the phone, so you need to find the phone, but you need also to have some context related to that. So the technical challenge of alignment, just as a reminder, is identifying those cross-modal correspondence and dependencies between elements from multiple modality. So the explicit alignment and the implicit alignment, will study both of them. There is some of the core that are similar, but in the case of explicit alignment, our goal is in itself to know what elements are connected with other ones. In the other one, in implicit alignment, the real goal may be more a representation that we learn, or even a task that we end up predicting. But in all cases, the core of it are those multimodal connections, how elements correspond to other elements from different modalities. And there is at least a spectrum that is maybe not an exhaustive list, but at least giving you some examples of connection types. At one extreme, you have the equivalence, like two elements are exactly equivalent, like there's no more information, like one and the other together, there will be no extra information gathered. Correspondence is, I will say, the bread and butter of language and vision research in the past years, has been like these elements or a word related to an object. And so there is a correspondence. Often the language is a description of what is in the image. So there's a very strong correspondence in it. And then dependencies is bring this complementary, or this temporal aspect of it. So you will have two elements that are dependent because one needs to happen before the other, for example. So equivalence, pure equivalence, is a little bit rare in multimodal. Often it's more correspondences, and you see grounding as an example. And dependencies is one aspect that I just want to give a few more example of that. Example of dependencies. So dependencies, there's at least two type of them, that at least that we'll discuss today. One is directional dependencies, where there is some kind of temporal contingency between two events, and maybe an analogy to syntactic dependencies you could imagine, as a if it helps, if your background is in LP. But also there's codependency. So two elements that together will maybe something will emerge from it. So these are a little bit more rare, but they're important as well. So codependencies doesn't mean that they're exactly the same, like corresponding, but if you bring the two together, there's something that comes out of it. So as a first sub-challenge is to learn these explicit alignment and identify these connection. And this has there's a long field of research in this. Some of them even here at NACL conference on grounding, how to connect elements, for example, of words. Usually grounding is related to language. So language meaning grounded in its environment, and a lot of it recently has been in connecting it with the words, with the image, so the objects. Um, and that's one key technical challenge of explicit alignment, is connecting them. And the second aspect of it is often in other certain modalities like speech or vision, when it's a video, it's not always clear what is an element? Like what is, sometimes it's clear because it's an object and we have defined over the past decades, or at least the past 10 or 15 years, that many objects are in fact a bounding box, which again is an approximation, but for now, for many systems, an object is a bounding box. And so that's one way to partition things. But in reality, partitioning is a component of alignment, because unless you have identified some elements, some unit that you can start processing, then it becomes very hard to do the alignment. One approach, so one of the challenges to do the alignment and at the same time doing the partitioning. So, for example, when you have signals, or if we have a video, and so you have video and you want to align two videos together, or a video with speech. In these kind of situation, the challenge is both alignment and segmentation. And one approach is to make it a many-to-many a warping almost between them. To say I will pick a sampling that is so high that I know at least that a unit will never be smaller than that, and then my goal will be to connect them, like which elements of that first modality connects to elements of that second modality. And if it's a sequence data, there's some well-established approaches. I just want to name probably the first one that everybody who think about explicit alignment should know about, which is dynamic time warping. This one is solving some dynamic programming, and mostly almost exploring the space of alignment, and then through this dynamic programming finding the best path, the optimal path of alignment, of warping these two. And there's nice extension of that that will also bring some of the earlier discussion about correlation and canonical correlation analysis as a way to enhance the multimodal aspect. Other people has decided to make it a prediction task. So I have one modality, and then for the other modality, I'm trying to predict and make it a prediction task. It would be in this case, back in the days was like maybe a CRF or an LSTM, and you make it a prediction task that, hey, which of the phoneme I'm in, and because it's phoneme, you could also have a silence, and then you will nicely find all the paths again, and then find the predicted that's the most likely labels. If you have a video or any modalities, another way to do alignment is, I call it the double translation or temporal consistency. The idea is that my frame, if this frame is really should be aligned with this other frame, then this frame should also think that I'm its closest one. So and if it's two modalities and you're modeling like speech and gesture, so that speech segment, if it thinks that it's the closest to this modality, then that visual frame should think that this is the closest acoustic frame for it. So this temporal consistency is really an interesting way to study. It's kind of a different way of studying the alignment. So just to show it visually for images, just because it's a little bit easier to visualize. If you have two videos and you want to align them, you want to align every frame. The idea as the first step is for every frame of the source, or let's call it the source video, I'm going to look at how close am I from all of the other frames from the other sequence. So in this case, because it's video, the same encoder will be used for both video sequences. If you have multimodal, then we'll have in fact two encoders that are learned at the same time. And so the encoders are trained in such a way that I want to have to solve that temporal consistency. So that frame, look at which of the other frames from the other sequence is the closest, and then pick the closest one, and then look back and say, hey, What do you think is the closest from your perspective? And if there is any kind of difference to it, then there's a penalty to that one, and you will want to reduce that as much as possible. And so these are examples of explicit alignment. There's also, for example, the idea of hard attention. But now I want to discuss what really became a field in itself, and both in unimodal and in multimodal, is the implicit alignment, where here you will solve the alignment as part of this kind of latent process, but really the goal is about learning representation over a structure. That's what it is. It's learning a representation over a structure. And in this kind of situation, the alignment is there to help, but because it's not the end goal, often it's going to be a soft alignment or soft assignment. You will often have it so that any element of one modality could be associated with any others, and then the real goal is really to learn the better representation. So in the case of you listening to me right now, you have language, vision, and acoustic, and you'd like to learn that representation over time, but taking into consideration all these correspondence and connection between gesture and emphasis, speech, vocal emphasis as well, and you want to learn this. And one of the simple approach, but very efficient and still should be seen as a strong baseline, is the idea of early fusion or concatenated. So what you will do is you will concatenate all three modalities, concatenate. So each of these modalities over time, you will concatenate them. Or if it is an image, you will take the image and you will simply make it as a list of objects. And then you will learn through this transformer, self-attention, that will really look at all possible pairs of all possible elements of each modalities and contextualize each of them with each other. You can see it. So let's look at it for the case of visual and language, which was one of the first that was proposed in that direction. Is that if you have an image and a caption, and you'd like image captioning in this case, like, so a person hits a ball with a tennis racket, you could do the training this, you could do the typical BERT approach for language, in this case by masking certain words, and by simply adding all the objects as well in there. And in this case, the object could also be masked as well. And then you just add your position embedding, you extend it a little bit to have that token image information, and then your transformer can be nicely trained through this. So this is with two modalities. You could do it even with three modalities, but everything is connected with everything. That does put a little bit of pressure on the transformer. So what seems to have worked a little bit better in the recent years is to not force everything early fusion, but make it as a cross-modal or cross-modal alignment. What it is if you have modality A and modality B, is see how can I contextualize modality B using modality A, and how can I contextualize modality A using modality B. So the transformers could be, in fact, you can have a separate one that looks at contextualizing A using B and B using A. In fact, if you have three modalities, then you can see it as each of the pairs being contextualized with each other. So if I have visual, how is the language can help me contextualize my visual? How can vocal also contextualize my visual? And all six combination. If you have visual, you contextualize with the other two modalities, and then you have a nice simple aggregation so that you get one representation from both contextualization. That is what you will do for each of the three modalities. You can do it over multiple blocks. And if you want at the end, you could bring all of them in one joint representation or keep them separate. That's also possible. I just want to show the example of what one of these cross-modal transformer module will look like. So in this case is visually contextualizing the verbal content. So I have the verbal content, the language. I like this tutorial. I like this. So I have my language, and so I have this representation of my language, that the word, a specific word that I would like to contextualize visually. And then what you will do is looking at similarity functions, the same kind of kernel, kind of attention kernel that we've seen also earlier when we discussed representation. So you want to look at similarities with all the frames. These will give you some attention weights, and then multiplied by the visual embedding itself, that will give you what is it that is correlated, what is this information that seems to be relevant from the visual side. And then the magic trick is that it's going to be a residual connection. What it means is, what is it that I was not yet in the language that the visual could add to it? And that becomes my new visually contextualized representation of language. In fact, many of the follow-up approaches all use that cross-modal transformer, and dedicated to go from language to vision and vision to language. This is Wilbert. Sometimes they add after that a unimodal transformer, but that's just a design decision. Similarly, you had the LX merge that also did the same with the cross-modal interaction there. These end up, although cross-modal, end up connecting almost every element to every element, so every word to every object. And so there's another family that I'd like to also broaden, is the aspect of graph networks. Graph networks could and can and bring a little bit more knowledge, possibly from if you have external knowledge about which node are likely to be connected with other nodes, or you want just the network to learn a structure inside your data and not necessarily have all possible node connected with all possible word with every possible images. Another aspect here is that similar in a transformer but more explicit is that it will allow to have different edge function for different connections. So if you have, for example, between modalities, maybe you have certain type of connection which will maybe model modal correspondence, and then temporally maybe you will want a different type of connection edge that will, in this case, model more of the dependencies. So graph could offer also a little bit more flexibility in that sense. So assume we have a graph. We know this representation. In fact, graphs have been used for many years, social network, but also another field. So you have vertices, you have your adjacency matrix, or the list of edges, and then this is a matrix of the nodes. And so you have potentially also all of labels for it. So you may have a graph like potentially it's fully connected of all possible words that has been spoken and all possible objects that are observed. That's where your X, and maybe there are certain knowledge or certain connections, or overall maybe you have a label for the whole network, and that's what will be your Y. So if you start and you have that kind of knowledge, and you know that certain nodes are connected only to certain other object or words, then you have to ask yourself, how do you encode that kind of graph representation into a more feed-forward neural network? And the key idea here is, in fact, if you have a graph, to in fact target one node at the time, one node, and then look at its neighbors, and neighbors from that, and in fact define one network that will take as input all of its connected nodes and finally give the output A. And this is a recursive manner, in fact, and for people like belief propagation, you have a flavor of that almost in that as well, for people who worked on this. So, so the nodes A and so the nodes B is in itself also connected to A and C, and so you will have multiple layers like this. In fact, at the end of the day, if you have 6 nodes, you will have 6 networks. And each of these networks will then repeat itself from layers to layers. So what looks like infinitely large and continue, because the structure is the same at every layers. In fact, the layers, although I display them as different, what it is in fact they will be a replication of each other. So the networks will repeat each other from layers to layers and to layers. And that is, in a sense, the idea is that instead of contextualizing every node with all other nodes, is that only a subset of nodes will be contextualized because of their neighbors. But over many iterations, many layers, all nodes are likely to be contextualized at some level, unless you have a graph that is not fully, that doesn't, you have 2 separate graphs in your networks. Um, so this is the idea of graph neural network, but the key question, the key technical question is, how do you aggregate information from the different neighbors? How do you aggregate multiple? And there have been many different interesting extensions on that. The original will have been just an average pooling of all of them, so you're simply averaging. And in fact, the early version had a different weights for yourself and from the neighbor nodes. The graph convolution network was a big, it was more efficient, different normalization also, but the same idea of the weight for both neighbor and yourself. So then, and finally the graph attention network that brings to it the attention weight, very similar to a transformer. If you make it fully connected, then it becomes a transformer at that point. And so if we revisit the multimodal problem, so then you would want to learn network. So you have a way of encoding each text or each sample or each token, similarly with the visual and acoustic. And then the second step will be the edge construction, where you will study 2 types of edge, the modal and the temporal edge. So you're studying, allowing edges for between modalities and temporally as well. And then there is, if you look more in the details, there's also ways of trying to prune the number of edges over time. So this is a summary of alignment that emphasizes both the explicit and the implicit alignment.